Hi, everybody. I'm David Greenberg. I'm here with some of our group and some guests at Hereon in a hybrid format for episode 31 of our ML seminar. We have a pretty interesting paper to discuss. It's applying machine learning to learn proxies of chemical computations in atmospheric models. I think this is very interesting for the approach they take, and it's also really worth just describing the problem because this is an extremely promising, fruitful problem to apply machine learning to in earth science. Before we get into this couple of papers, mainly we'll focus on this random forest paper, focusing on GEOS. There's a second paper using deep learning we'll get to at the end. Very briefly, I just want to announce that we are hiring a postdoc in our group, and the deadline is August 29th. You can look on our website, m-dml.org, for details, and we'd be happy if you told your friends as well. So, chemistry in atmospheric models. I want to describe briefly the nature of the model, the problem setup, and then we'll get into how this group approached the problem. So we have a similar scenario to what we've seen in a lot of previous models. We have dynamics, so basically the compressible Navier-Stokes equations. We have emissions of various chemicals from different points in space at different times. We have subgrid parameterizations, everything from turbulence to radiation to orographic drag to many other things. We have photolysis, which this is something new that we haven't seen in the climate and weather models we've looked at here. Based on the radiation incoming variables like the solar zenith angle and so on, and the prevalence of various chemicals in the atmosphere at each location, we're going to calculate rates at which certain light-driven chemical reactions take place. And so then we have our chemical integrator. Based on the atmospheric conditions, all these meteorological variables like pressure, like temperature, like various kinds of moisture, we are going to have reaction rates. And these rates will describe the rate, you can see this equation here, at which various chemical species are gained or lost at that location. So if CI is the concentration of species I from a long list, which we'll get into in the next slide, we have the production rate of that species as a function of all the conditions. We have the loss rate as well as a function of all the conditions multiplied by the current concentration and the rate at which the current reservoir, that location, is lost. So we have all these changes. Now, these are not the only things that cause changes in chemical concentrations. You also have transport. For example, you have emissions and you have deposition. But what the target of this current study is this equation here, which is also by far the most expensive part of these coupled chemistry atmosphere models, right? So in this case, we're looking at a GeosChem open source atmospheric chemistry model, which includes dynamics and chemistry and some other parameterizations. We have a 50-minute time step. We're modeling all of July 2013. We're using a cube sphere grid, which we covered in episode 2. We have 72 pressure Z levels, and the chemistry is performed at each location so we can deal with each grid cell and Z level independently. Now, in the mode in which they run this, and where they want to develop the machine learning proxies for the chemical integrator, we are not using feedback from chemistry to meteorology, so that the meteorological variables, again, wind speed, temperature, pressure, and so on, moisture above all, affect the reaction rates. The prevalence of chemicals does not affect the meteorological variables. There's no effect on precipitation, on temperature changes, on convection, which is not realistic, but it allows them, as they mention in the paper, to really focus on this effect of meteorology on chemistry. So they want to separate this from feedback effects. We can debate this later, whether this is a reasonable and good choice. But this is the overall scenario. What we won't get into, but I'll just mention briefly, is the chemical integrator, having defined these differential equations, then actually needs to solve them. It uses a Rosenbrock solver that's an implicit method. which is expensive and can take well over half the total computation time of these coupled atmospheric and chemistry models. For example, ICON ART, which is being worked on extensively at KIT. So this is a setup. What we want to do is replace the chemical integrator with a machine learning method. So what are the inputs and outputs? The outputs are basically updates to 51 chemical concentrations, everything from ozone to nitric oxide to a bunch of other things, some aerosols. The inputs are those same 51 concentrations on the previous time step, but other variables as well: photolysis rates, temperature, solar zenith angle, humidity, pressure, density, and the amounts of moisture in cloud, vapor, liquid, and ice forms. So this is a setup, and this is what we want to reproduce. What is our strategy here? So actually, I'm sorry, before I go into that, I want to go into a little more detail about the nature of these models. This is pulled from the GeosChem GitHub. So this looks a little intimidating. I'm going to just talk about what I'm showing on the screen. On the top, we have just maybe 20 lines of code from thousands and thousands describing the 400 reactions which are described by the chemistry in this model. So on the leftmost column, we have a human readable form of the reaction. For example, line 464, 1 ozone, 1 nitrite goes to 1 oxygen and 1 nitrate. Okay, so in the left column, we have the chemical formula. In the next column, we have either a value, which is the reaction kinetic rate constant, or we have a function call, which will take in various constants and allow things such as temperature dependence of the reaction in the case of gas phase chemistry. So we have, for example, this GCARR, this is the Arrhenius function, and we say we have the rate is a function of some constants which are input, and they can be different for each reaction, and it's also a function of the temperature. And this exponential dependence on temperature is a very common feature of kinetic rate constants in chemistry. But this is a simple case. This is gas chemistry. We have several hundred reactions like this, but we also have a decent number of what they call heterogeneous phase chemistry, chemistry happening inside of droplets or on the surface of ice crystals and so on. And here you see a function called for such, this is a cloud head function, one of several of these heterogeneous phase chemistry functions. And you can see there's many more inputs, right? You have these constants to determine the rate, but you also have things like the amount of ice, the amount of liquid water, and a whole bunch of other constants. So you have some very complicated relationships modeled between the environmental conditions described by the outer dynamical model and the reaction rates for these different chemical reactions. So this is basically how it looks. And you can look at this file, you can edit it yourself. This is KPP, Kinetic Preprocessor, which is a tool which will take this equation file and basically automatically create a Fortran file to calculate, if I go back a slide, the rates for these differential equations and solve them based on this human readable description of the reactions. So this is what we have to work with. This is what we want our machine learning method to imitate, and to do so in a way which relieves some of the immense computational burden of modeling these hundreds of reactions and chemical species over a large grid. So how do we do this? This paper uses random forests, which we first saw in episode 19 and again in episode 21. So you can go back to episode 19 on YouTube for a complete review of this. And if anyone has questions, just pipe up in the Zoom chat anytime. And essentially, we construct these trees where, given all our input variables, our 126 inputs, we're going to choose a random subset of these. We're going to choose an ideal variable to threshold, and in order to give us the most information about the output, we're going to repeat this process so we get many branches of the tree. We're going to repeat this several times for different groups of variables, and we're going to average the results. So details in episode 19. But this is a nice method for several reasons. It keeps its output within the range of the training data, so it can never go off to infinity or negative infinity with unexpected data. And it's pretty straightforward to train, and there's a nice scikit-learn implementation, which these guys used. So they're building a different random forest for each of our 51 outputs, which we want to predict. We want to predict the updates for 51 chemical species, right? And so we're building a random forest consisting of 30 trees with 10,000 leaves for each of these 51 outputs. They're using a few other tricks, but this is a basic idea, right? Instead of running everything, okay, we have our compressible Navier-Stokes, we have emissions, we have our parameterization subgrid, we have photolysis, our chemical integration, deposition, and so on, record our data. Instead, we're just going to replace the phase where we use the chemical integration, this expensive chemical computational step, with a random forest. I should say, I actually meant to mention this earlier, but one of the most impressive things about this GeosChem model is actually the emissions step. If you look at the documentation, the emissions, basically where they're putting new chemicals into the model, they're using basically maps of where wildfires tend to occur, maps of airline travel, maps of ship transport, maps of emissions from cities. So there's a lot of data that goes into that. It's a very sophisticated model. Okay, and what are the other tricks they get to use is they get in order to make this this work, to predict the changes in the chemistry accurately? One thing is, so for long-lived species that tend to stick around for a while, I believe ozone is in this category, they predict changes in the species instead of the new value of the concentration. So instead of predicting the new concentration, they'll predict the change in concentration. This gives better results. However, for short-lived species that only will last a few time steps before being consumed, they're going to give the new value. I think the logic being that the previous value is not as informative. When you run the chemical integration for 15 minutes, the initial conditions aren't as important. And for very short-lived species, it might only last less than a single time step as an intermediate, a chemical intermediate between the inputs and the outputs. They're not going to model those concentrations at all. You're just going to kind of implicitly include them from the inputs to the outputs of the 51 species they do model out of maybe some 150 they could model. And then finally, they're going to group together similar compounds. For example, nitric oxide and nitrate get in this NOx category, and they find this improves performance. Okay, so how does this work? We deal with this typical coupling problem, as in a lot of previous machine learning proxies we've seen. We're learning a proxy for one step of this long chain of computations. We're building a machine learning model. We like to train a chemical integration proxy which leads to long-term numerical stability and accuracy when coupled to everything else, the transport emissions, parameterizations, photolysis, and so on. We can't do that because we can't take into account the feedbacks between what we're learning and the rest of the model during training. What we can do instead is train on single time steps. We know what the inputs and outputs should be from running the full model with the expensive chemical integrations. And so we're going to use it as training data. We can test the results by coupling it back to the outer model after training, but we can't incorporate the effects of this coupling during training and incorporate that in our learning. This is the coupling problem, which really plays a lot of our efforts to use machine learning in a physical modeling context in earth science. So what have they done? I'm going to show two examples. Prediction of the ozone tendency, that is a change in ozone, and prediction of this NOx category, which is just a nitric oxide and nitrate, which are both also related to ozone chemistry. So what do we have? First, on the left, we have all these trees, right? And when we're building the trees, we're selecting the feature out of some randomly selected group, which gives the best improvement in performance when we make the cut there, when we threshold that particular feature. And this importance basically just asks, how often do we threshold each feature when we intend to build this tree? And we can see that for predicting ozone, one of the most important features that occurs in most of the trees of the random forest is nitric oxide, which is, if we look back to our very top list of reactions, we can see indeed nitrates and nitric oxide are indeed very involved in ozone chemistry. So this is not surprising. This is it physically makes sense. we can also see that some of these input features are photolysis rates. These are some of the 126 input features. Anything with the arrow indicates photolysis. And this is also expected, right? Because we know that photolysis plays an important role in ozone chemistry. So these are the features that were selected when we built our random forest using scikit-learn. And then here is the performance over single time steps. The true tendency in I guess, parts per billion, I'm not sure what the V stands for, is on the x-axis, and then the prediction from the random forest is on the y-axis. Again, you can see this nice feature of random forests, that their predictions always stay within the range of the training data, so we don't see any extreme outliers like we might see with an overfit neural network. And overall, we get a pretty good fit. Not every prediction is perfect, but our R-squared is 0.95. We're training on 2.5 million points, taking advantage of the fact that every grid level and every grid location is an independent data point. Similarly, for the NOx group, we see a much lesser influence of photolysis. We see ozone is involved. We see nitride itself is involved, and nitric oxide, unsurprisingly, and some things undergo reactions with them. We see also pretty good prediction here for single time steps. So what we're seeing here overall is that by taking into account these features and building a decision tree, we can get a pretty decent prediction of the changes in the concentration of these chemical species. What happens now, and this is always a big test with these models trained on single time steps, what happens when we try to do predictions over multiple time steps? And it's a mixed bag. Overall, it's better than we'd expect from a lot of these other papers, but it's not perfect. So what do we see? I'll do the right-hand side. First, we're looking at ozone. Here in the top row, we have the GeosChem model. This is the target. This is what we want, right? And here we see the coupled, so one-way coupled chemistry and atmosphere. One-way coupled in the atmosphere, the meteorology and the emissions influence the chemistry, but not the other way around. And we can see the concentration of ozone here after running for 5 days and 10 days and 30 days. We see some accumulation in this case over in July 2013 over North America, over Asia, a bit in Southern Africa. Okay, and this is what's happening. We look at the random forest, we see the overall, the same trends, especially in the more densely populated areas where the emissions are happening. And we see some diversions as well. If we look at the difference divided by the true value, we see the errors are mainly a positive bias. We tend to have too much accumulation of ozone. And we have this in not what you'd expect, not where ozone is maybe most accumulated, but we have it in places like the remote Pacific Ocean. And the explanation that the authors give for this is that in locations with a lot of chemistry happening, with a lot of emissions, the initial conditions aren't so important. So errors really don't accumulate over time. It's the chemistry and the emissions which determine what the concentrations look like. But in places like the Pacific, the remote Pacific, there's not as much chemistry happening. And things kind of pile up slowly. So that if you have errors, they tend to accumulate over time. They don't get overwritten by new chemistry and new emissions. And indeed, if you look at the places they chose to evaluate the time series, New York, Delhi, London, and Beijing, well, these indeed are places with lots of emission and lots of atmospheric chemistry happening. So there's going to be less of the sensitivity to initial conditions, again, especially because they only couple one way from meteorology to chemistry, but not backwards. We see a similar picture if we look at our NOx group, the nitric oxide, nitrite, and maybe nitrate, I'm not sure. But we see a pretty good match in densely populated areas in Europe, in North America, and so on. We see less of a good match in the Pacific Ocean and the Indian Ocean, and so on. But overall, we can see a good match in the time series in both cases between the true underlying model we used as training data, GeosChem, the random forest, although we see some divergence. For example, the random forest seems to underestimate the nitrogen species in New York for some reason at certain times. But it's much better than having no chemistry at all and just using emissions and transport. So we're getting somewhere, it's numerically stable, it doesn't blow up completely, and it gives a reasonable answer, at least in some places, even after a month of integration, which is impressive considering it was trained on 15-minute time steps. Okay, some concluding thoughts. I like this problem a lot. Similar to the cloud physics, cloud microphysics we covered, Cypher and RASP, a nice thing about these parameterizations is that while they can be run coupled to the model, you can run them in a sensible way and produce meaningful results in a kind of a box model mode, where you're just, basically running it without any transport, without any Navier-Stokes, and letting things accumulate over time. This allows you to take numerical stability and accuracy for multiple time steps into account without being able to differentiate through or have a machine learning proxy for your entire model. Another really nice thing here is that we know the computational costs of the targeted processes, in this case, the chemical integration with our implicit Rosenbrock solver, hundreds of species, 400 reactions. They're really high costs computationally. And it's also not obvious you can speed them up with a GPU or any other clever tricks. Having a machine learning proxy could be really effective. The models are available, they're open source, they're actively developed, there's GitHubs with a lot of branches and issues and forks, and they're well documented. There's been some progress here, but it's pretty new. As the authors note, there's some chemical principles that haven't been exploited, right? We're learning these updates, but we aren't taking into account the chemical formulas. So indeed, if every reaction, just to take a very simple, absurd example, if every reaction which produces an ozone, for example, or say which consumes an ozone also consumes an NO2, if we only had this reaction, then there would be some relationship between changes in ozone and changes in nitrate. But this kind of information, these molecular ratios encoded by the chemical equations, is not yet taken into account, but it could be if someone could come up with a clever way of getting the neural network to respect that. So yeah, it's a very promising problem. It's a very exciting problem to work on. It's nice to compare this to some other stuff we've seen. The random forest is nice. It seems to be more stable. We saw this with Yuval et al. Also doing this for atmospheric parameterizations of I believe it was some turbulent heat exchange. I'm probably getting this quite wrong, but where they use random forest there as well, they got much more stable results for multiple time steps than with deep neural networks. They did a pretty good job in terms of they have a high dimensional input, high dimensional output, but they still managed to get it to work. The sad story here is, do I have these numbers? Did I put them in? I'm not sure. No, the sad story is it's not that fast. Because they're using separate random forests for each output, they have 51 outputs, 30 trees, 10,000 leaves. It's actually somewhat slower than the original model. They acknowledge this, and I think it's okay. They showed that it's possible. And I think if someone now wanted to come along and put these things on the GPU, optimize them a little bit more, reduce the number of trees or leaves, it's probably possible, but it's a start. In a way, they've gotten some stable results over a whole month. I think I'll leave this to the question phase, but I would question how well they've really come up with a solution to the problem of coupling over time for parameterization learning. So these are my thoughts on Keller and Evans. I think we'll have quite a short episode today. I'm just going to, that means plenty of time for questions. I hope someone's keeping an eye on the Zoom chat in case we have any questions. Now we could take some. But then I will just go over a couple slides on this previous paper, Kelp et al., which used a different approach. So they're looking at a different model. I'm not going to go into the details, but I think it's substantially similar to GeosChem. CBMZ has you can couple it to dynamics and transport and so on, and radiation, photolysis. It has chemical reactions. It's in Fortran. But instead of using a random forest, they're going to use a deep neural network. And the advantage there indeed is they learn a set of features. They can use this to get all the outputs at once. It's much more efficient. They use a few deep learning tricks, nothing too fancy. They normalize the inputs so that they are Gaussian distributed through a transformation. They have ReLU networks. They do batch norm. They have residual blocks, but they're fully connected, no convolutions. They have skip connections, and that's basically it. So they get a really, really fast neural network. If you look at the time for, they're saying chemistry for 1 million grid cells, we're talking about 20 minutes or so for the original CPU implementation. We're down to about 8 seconds for the neural network on the CPU, 2 seconds on 8 CPUs, and then finally, less than half a second for a GPU. So we're really getting, as they claim in their title and emphasize very, very emphatically, is they get several orders of magnitude speed up, and they're getting similarly accurate results for single time steps. Unfortunately, unlike the random forest, it's not as accurate over many time steps. Here you can see O3, the error in ozone. They're starting at midnight and they're just running it for 24 hours. You can see the errors really accumulate fairly quickly. And you can see, if you look at a whole bunch of different chemical species, some of them work pretty well. They all work pretty well in the beginning, as you'd expect, because we're training on single time steps, but at some point things diverge. At some point errors accumulate and we can get completely different results. Sometimes correlations can even be negative between the original CBZ model and the outputs that they are outputting using the self-iterated neural network. So we have kind of 2 papers here. One of them showed you can learn an accurate proxy, but maybe not very quickly with the tools they used. The other showed you can get a very fast proxy, but not quite accurate and stable over many time steps. So as I said, it's a very promising problem. There's a lot attractive about it as something to work on. We're just starting to see a few papers making progress. It can be used in box model mode or coupled to dynamics. And yeah, the ingredients are there, but we don't quite have something where we say, okay, go and replace your chemistry in your weather climate model yet. So that's about all I have. We can take some questions. We can discuss a little bit. I have 1 or 2 more comments. I want to open it up first. Anyone on Zoom have anything to say? Either chime in on the audio or write a bit of text. Well, I'll say one thing, which is what I was going to say about the coupling problem. So they're coupling one way. And they have a model which is, at least in some places, not so sensitive to the initial conditions, because new chemistry is happening and new emissions are happening. After enough time, it's the opposite of, say, for example, this atmospheric chaos, where the initial conditions can really change the results a lot. We have a challenging task in that we have to compute over many time steps. And we have sort of a coupling problem there. But because the results don't depend on the very distant past, it seems, maybe in places like the remote Pacific a little bit, but certainly not in these cities where you'd like to predict air quality. Because of that, the coupling problem is much less severe. And what might work here, like a random forest, trained on single time steps, isn't likely, I think, to work over much longer time scales for parameterizations which really have to feed back and affect the dynamics, like turbulence, like microphysics, like convection, even like chemistry, if you wanted to run it in maybe a long-term climate mode and really look at the effects of chemistry on atmospheric dynamics as well. So we've got progress, but I think the coupling problem is just as open here as it always was. Hopefully some input or questions or comments or opinions from someone else.
Would it be possible to stabilize the neural network by, explicitly telling it to be more stable or to respect long-term stability more in the loss function direction? You feed it a sequence of inputs of chemical concentrations and ask it to predict one new tendency from that rather than only looking at the last time step.
You could. I mean, in theory, let's see. Yeah, you can look at multiple time steps in the past or multiple time steps in the future. In practice, this can help, but in theory, at least, if you look at the way the model computes information for the new update, all the information you would ever want to predict the next time step is already in the current time step. The model doesn't look in the past. Now, in practice, those previous time steps are going to be correlated with the future in a way and may provide more information, especially if your training data is limited. It might help you to take that into account. The other direction is also very interesting. So what if you ask the model to predict one output and then you feed that back in, say in a box model mode, where you don't have any spatial transport, and you try to predict several future outputs, then this is beginning to look a little bit like a neural ordinary differential equation, as we covered in some recent episode. I'm not quite sure which one. Yeah, you can take into account multiple time steps during your training. You absolutely could do that. I think it's something that's talked about. I don't think it's really been done for any parameterization learning in any weather or climate model scenario that I know of. It has been done a little bit in fluid dynamics and that kind of stuff. Yeah. So yeah, episode 26, we covered ODEs. I mean, there's also a possibility of enforcing stability some other way, besides looking at multiple future time points, just saying that if you, so even not looking at any data, if you put the outputs back in as inputs many times, it shouldn't go to infinity. Maybe there's some way of enforcing that. I don't think anyone's come up with this.
Do the authors mention any way, like why do they use residual blocks of these networks? I mean, that's not something we see a lot when we use fully connected networks.
Maybe I'll turn that to you, Shivani. You did something not too dissimilar, right? You learned updates instead of, I guess it's not quite the same thing.
Yeah.
But
if you're talking about learning updates instead of learning the next value itself, this, I think they have also mentioned it for I think one of the papers, right? They mentioned that they also realized, at least for the chemical species, which had a certain value for a longer period of time, it was better to, they got better results when they tried to predict using the neural network the change from the previous time step instead of the absolute value.
right. You're right. That's not quite the same as residual blocks. Don't know. Yeah, I mean, the logic of them even when you don't have convolutions, is kind of there, right? You can use deeper networks and you get better optimization.
The updates are smaller, sure.
Right.
Yeah, I just find this interesting because I think I haven't seen it before, but this might be my very limited view in the literature.
If you think of a ReLU unit having two modes, right, where it transmits information or it's blocked, in the case of just a simple ReLU network with no residual blocks, then when the ReLU when the input goes negative and it goes blocked, it just transmits 0. Whereas for the residual block, when the ReLU's input is negative, then it transmits the identity function. It transmits its input back as output. So this might be like a slightly nicer feature, that when you either give a linear function of your input plus the input, or you just give the identity. Whereas without the residual blocks, you either give a linear function of your input or nothing. So this might, it might make training with deeper, wider nets behave a little more nicely and the optimization work a bit better. Yeah, but I agree, you mainly see these in confidence. The other thing one has is it's a short archive paper. The second one is also, I think it's nice work, and I expect more from that group on the topic, but it wasn't very detailed, and they didn't, for example, try out alternatives. I don't think they tried out the variation where there were no residual blocks. They didn't do an exhaustive search. And maybe the first thing they tried and it just worked for single time steps.
Well, it would be nice to have a comparison with a neural network which does not have any residual blocks in it, and to see if actually adding residual blocks is improving the results by which degree.
Yeah, I would also have to check how deep their networks actually are. Let's see, I mean, yeah. Inputs, normalized, single fully connected layer, 4 residual blocks with 2 fully connected layers. But okay, so we're talking about 9 or 10 layers. This is the point where residual blocks might help a little, but you can certainly train a 9 or 10 layer network without residual blocks, right? I mean, the ResNet paper, hey, 2015 was starting to talk about 120 layers. Any other thoughts, any other questions? It would be great to hear from someone who's worked with atmospheric chemistry, what they think about this. We have a question from Kubi. He's raising his hand. Yeah.
Yeah, so my question is, so you are talking about how sometimes the model violates the chemical reactions in a way that you have some 2 different components that change, but maybe one is changed differently from the other one. So my question is it possible to somehow control this violation of the chemical reactions, but not increase the numerical cost too much, or the computational cost too much?
I mean,
and is there some idea out there?
Yeah. I'm sorry. One possibility would be, instead of outputting 51 chemical concentrations, the random forest or neural network could output 400 reaction rates. And then if you multiply that by the the coefficients on the left and right hand side of each chemical reaction, and then multiply that by the time step, then you get updates to each chemical concentration. That would be very attractive if you had maybe, 25 reactions with 100 species. If you have 400 reactions with 150 species, as you have here, well, now you're using more outputs than you would if you just learned the tendencies. This also recalls this distinction we saw in Yuval's paper, episode 19, where instead of learning tendencies, and I believe it was the moisture in a vertical column of their model, they learn fluxes. And then by using fluxes instead of tendencies, they automatically get conservation of mass. But there, I mean, they actually have a similar number of tendencies and fluxes. Here, the number of reactions is higher than the number of chemical species. So it's questionable whether this is such a good idea. But it would be worth a try.
Okay, thanks. It's definitely interesting what different possibilities there are out there.
Great. Any other questions or comments before we close? Okay, thanks everyone very much for joining. We welcome suggestions for future papers. Let us know if you want to present your work for 5 minutes. Thanks again and see you in